I have my graph written. It's now time to do the depth first traversal. And the thing that's really interesting is, if you think about it, when I'm traversing a graph, I need to color the vertices, but I don't need to maintain those colors in the graph itself. I'm going to take advantage of the fact that I can create a separate class to manage my depth first traversal of the graph. That graph is going to be maintaining the coloring scheme. And then I keep my graph over here as a pristine data structure to record the structure of the graph. Let's get started. To do a depth first traversal, I'm going to create a class called depth first traversal. What does this class do? Well, it needs to remember the state of the traversal. And it's going to start with an init. That starts everything off. And when you traverse a graph, you actually need to have the graph, of course. And you need to have a start vertex, which is where you're going to begin your search. So this initiates a depth first search traversal of the graph. When that depth first traversal is done, what really has been accomplished? Well, if you reflect on the pseudocode I showed earlier, it builds up a predecessor link. So I can keep track of where I've come from, so that if I wanted to, I can find the path from the source to any other vertex in the graph. That's a very useful thing to have. The analogy I showed earlier was with a maze, where you want to start from a certain location and go to a known target location, at which point you stop. But a depth first traversal will explore the entire graph, not stopping until the whole graph has been covered. In fact, not stopping until all vertices are colored black. And that's the reason why I can't just use the gray nodes to figure out what my solution is. When the depth first search completes, I've traversed all the nodes in the graph, and now I can go through, and for any vertex in the graph, I can find the path from the source to that vertex. So for this, I need to record some information. Naturally, I need to keep track of my graph. I need to keep track of the starting location, which is that vertex that was passed in. I need to keep track of the colors. And for now, I'm just going to use an associative dictionary to keep track of the color with each vertex. And as mentioned earlier, I need to keep track of the predecessor link for every vertex, so I can know how to recover the path that was discovered in the traversal. We'll actually do everything here. This constructor might as well do all the hard work. And what I want to do is start with the initial state, which, as you might remember, I've got to color all the vertices white, and I've got to set the links so they all refer to none. Well, for this to work, I need to have some constants. And so I might as well say white is 0, that seems the default. Gray is 1, and black is 2. It doesn't really matter what those constants are, because I don't really convert from one to the other. They're all just special constants. And now what do I want to do? To initialize the depth first search, for all the vertices in the graph, and I can do that by traversing all the keys of my edges, as you see there. For all the vertices in the graph, what do I want to do? Well, I want to make sure that the color is white, which I now set, but I also want to make sure that I have no predecessor. I want to set things up clean. This will do that, and if you reflect on the performance of that, it's going to do order n, right? I've got n vertices in the graph. I just have to mark all of them as white and clear out the predecessor links. What I do then is I do a depth first traversal using DFS visit. I want to start with the starting vertex that was given to me. And now this DFS visit is the recursive function that we now need to implement to complete the depth first traversal. Let's show how we do that. DFS visit. It's going to take a vertex. I'm going to call it vertex u. This is a recursive traversal of graph using DFS. The first thing we do is, visiting this node, we need to mark its color to reflect the fact that it's now been visited. Fortunately, I have that color all set to go, and I mark it as being gray. When we're done with the depth first search, the very last thing I'm going to do is mark it as black. That tells me that I'm now completely done with that vertex. However, I still have steps to do. I need to visit all the neighbors of U that have not yet been visited. Okay, this is not that challenging to do. What we want to do is say the following. For every vertex that happens to be a neighbor of U, I need to check. Have I visited that vertex yet? And that's easy to do. If it turns out that the color of that vertex is white, I know that it's unvisited. Once I've determined that this neighbor V is unvisited, then I have to remember the fact that at vertex V, the predecessor is U. What that means is in any potential solution, I went from U to V. Once I've marked that, I continue my DFS visit, this time from V. When this DFS visit completes, it means that that entire graph has been explored, as many vertices as it took. When it comes back, I continue my for loop, which after all is visiting all the neighbors of that vertex U. So you can see how depth first search takes advantage of the backtracking which comes with the recursive function. Whenever a recursive function returns, it's essentially backtracking to an earlier step in the process. Whenever the recursive function calls itself, it's making forward progress. And so the code itself is quite small in what it's being asked to do. It always has to color vertices, starting with the initial case that they're all white. The following, whenever you visit one, you mark it as gray, and when you're done, you mark it as black. Now when you look at this, the first thing that comes to mind with the recursive function always must be, how do I know that it's going to terminate? How do I know it's not going to run forever? Well, we have some things at our disposal. We know that all the vertices are initially colored white. There are n of them. We know whenever you call DFS visit, the first thing you do is mark it as gray. And that means that you are never going to call DFS visit on that vertex again. So how many times can I call DFS visit? Well, no more than n times. And when I'm done, I mark it as black to clarify that it has now been totally explored. So I have, at least in a hand-waving form, try to explain that DFS visit as a recursive function will terminate, won't run forever, and how many times does it call, how many times does it recurse through, is based solely on how many times an edge is aligned with an unvisited neighbor. Once the depth first search has completed, you have recorded in the pred array all the information that's needed to recover a path from that source to any other vertex, as long as you follow a very simple approach. So let's define a function called solution, which takes a vertex V and says recover the path from the start to this vertex V. It's because we want to be able to recover the path from start that I had to record start when the depth first search was first initiated. So that here, when I call the solution, I don't have to worry about remembering it. It's already been stored. So I start by saying, well, what if you look for a solution from the source to itself? What is the empty path going to look like? Well, we have a couple choices. I'm going to prefer by saying maybe it's none, or maybe it's the empty path. So how do I discriminate these two? I'm going to use the following. If it turns out that V is not even a vertex in the graph, and I can do that again, check as I've shown before, under that circumstance, I'm going to return none. So I'm going to use none to reflect the fact that this isn't even a vertex. So this solution, there is no solution. When I want to determine the solution to an actual vertex that exists in the graph, let's start with the path, and I'll start with that vertex. Assuming that I want to get to that vertex, it must be in the path. So that'll be my first entry in the path. And when I'm done, I'm going to return this path to the caller. So the path is going to be recorded as a Python list of consecutive vertices that were visited from the start to this particular vertex. How do I uncover this? Well, you start with the idea that says, as long as I am not at the start where the DFS was initiated, I've got some work to do. Namely, that work is to go back and define the predecessor that got me to V in the first place. Once I have that predecessor, I'm going to append that to V. And we have a choice here. Do I want to reflect the path in the order from the source all the way to where I am? Or do I want to reflect it in reverse order? And I'm realizing now I want to reflect it in the order that I went. So I'm going to insert this at the beginning. Insert at the 0th index location that vertex. And then it continues until eventually you get your way back to that start vertex. So this is a convenient way of capturing the information in the graph. I'll start with my simple graph, which I've demonstrated I can construct anytime I want. And I want to do a depth first search over that simple graph. Now, you may remember what the simple graph looks like. It's this little graph here. And so if I start at vertex 3, I can reach all the other vertices in the graph. That's something that's easy to see. So I'm going to say, give me a depth first traversal over this graph, starting at vertex 3. Naturally, as we always expect, there's always a defect lurking here that we have to attend to. Once again, I go back and look at the code. In my depth first search visit, I'm asking for this edges. Unfortunately, edges is an attribute of the graph, not of the depth first search. So I have to say self.graph.edges so I can uncover the appropriate edges. And we'll try that again. Creating my graph, doing the depth first search. What I now wonder is, well, what's the solution that was created because of that? And if this is my graph, as you see there, well, starting from 3, I wonder, what's the path to get to vertex 1? Well, let's look for the solution to vertex 1. It looks like I went from 3 to 1. That's easy enough. What about if I want to go to vertex 4? It looks like I went 3 to 1 to 2 to 4. That's OK, because I could either gone 3, 1, 2, 4, or 3, 1, 5, 4. Let's look at the solution when I go to 5. Well, it's certainly taken the roundabout way, 3, 1, 2, 4, 5, a total of 4 different edges, when in fact it could have gone 3, 1, 5. But that's the nature of depth first search, and it produces a solution, which is what I was looking for, namely that it produces a path from the source to any vertex in the graph that demonstrates a solution was found. Now, I did want to mention one last caveat. It may be the case that when you do the depth first traversal, you have a graph which is not connected. By that I mean, what if you had a graph over here which had 2 separate components that were connected, but they themselves did not meet? What if I had a graph consisting of the edge 4 and 5, and then a graph consisting of the edges 3, 1, and 2? So those are 2 totally separate graphs, and they didn't actually have anything in common with each other. In that circumstance, it's not possible to traverse from vertex V3 all the way to these because these edges are not there. This is not a problem. We're just revealing an assumption that we'd been making. Namely, we had assumed that our graph was fully connected, which meant that you can get from any vertex to any other vertex simply by traversing the edges that exist. That assumption is invalid. And so we have to make 2 small changes to our code to reflect that. Let's first focus on what the DFS does. The depth first traversal, if you remember, the first thing it does is it goes through and it colors the vertices, and then it assigns the predecessors for each one. If I look at the DFS predecessor, I've got a bunch of information there. You can see how in this graph there is no predecessor for 3 because after all that's where I started from. So it keeps track of the very simple information. In the exact same way, when you go to do a depth first traversal, if there is no way to literally get from this vertex to that vertex, then the predecessor will be none. So the only thing I need to change in my code over here is not just check to see if this is the case, but to also check to say the following. If self predecessor of v is none, then I return none. It's a small, simple check, but I have to do it because if I actually had a disconnected graph, this while loop would run forever. It would keep trying to follow the predecessor links all the way back until it got to the start. But unfortunately, there isn't any, so it would run forever. So that's the one little change you have to make for the traversal. We can demonstrate this rather easily by doing the following. If I have a graph and I add two edges, 1, 2, and then an edge 4, 5. I've got a graph that has 4 vertices, but they are not connected. I can only go from 1 to 2 and back again. I can only go from 4 to 5 and back again. So if I were to do a depth first traversal of this graph, starting from 1, then what's the solution when I want to go to vertex 2? It tells me I go 1 to 2. That's nice. What's the solution when I go to 4? It's not reachable. So at least I've been able to clarify that point in the solution is working properly. Now if I were to do another depth of traversal from 4, I'd be able to encounter the solution from 4 to 5 and back again, and that would be separate from the 1 to 2 and back again. So we have now completed an implementation of graph that uses the adjacency list representation. As you can see, it allows you to store any number of edges with the vertices. It protects you from inadvertently adding the same edge or vertex twice. It offers a depth-first traversal capability that allows you to traverse the graph efficiently using recursion without running into any infinite cycles. It allows you to traverse from any source vertex to any other vertex, and it will encode the path for all of those. So from a single source, you can find the path to any other vertex in the graph. To summarize depth-first search, it is a blind search over a graph. Allows you to start from any vertex in the graph and traverse the known edges to reach all parts of the graph. It makes sure that the recursion isn't infinite by coloring appropriately to make sure you don't visit the same vertex twice. However, it's a blind search, and so it may end up with solutions that are much longer than ever is necessary. There's another companion algorithm known as breadth-first search, which you can read up on. It uses the exact same coloring scheme that we mentioned, coloring the vertices white, gray, and black. It chooses a different approach, however. It chooses to only visit vertices in a strict procedural way. First, vertices that are 1 edge away from the start, and then vertices that are 2 edges away from the start, and so on. With this approach, breadth-first search will guarantee the shortest solution. And so if that's what you're interested in, by all means, look at the breadth-first search. Depth-first search is a way of rapidly coming up with a solution without any real intelligence, just blindly searching the graph, and is usually satisfactory for most cases. This concludes the module on depth-first search.